Now, every example that we did, we neglected friction or wind resistance. Well, that's not always doable there. If a leaf falls off the tree, you'll notice that leaf floating in the air. The reason it's floating in the air, why? The wind blocking it. Or somebody in a parachute coming down. They don't just drop to the ground. They glide to the ground. Why? Because of the wind. So we need to figure a way how to include these non-conservative forces like friction, wind resistance, springs. These forces actually, we've been neglecting them the entire time. In this section, we're going to bring them in and see what will happen. So the work done by non-conservative force, it's really you take the change in the energy, mechanical energy. It is the final minus the initial. And these two normally don't equal to each other when there's a friction. They will not equal to each other if there's a friction or wind resistance. So let's take, again, here we go. We got that tree here, fig tree. I like figs. Have leaves on them, big leaves. And the leaf is 17 grams. Here's a leaf of a fig tree. Somehow get off the tree and it's falling down. The mass of the leaf is 17 grams. And drop straight to the ground. Its initial height, let's take the initial height of the leaf. So that's the initial height, y sub 0, or h of 0, whatever you want to call it. 5.3 meters. And the speed on landing was 1.3 meters per second. So when that leaf fell off the tree, what was the initial speed of the leaf? 0. Now right before it hits the ground, it has a final speed of 1.3 meters per second. Right before it hits the ground. And what was the height right before it hits the ground? Right before. If I use the ground as reference, how high above the ground? What, 1 millimeter? We're not going to use that, we'll just use 0. Because right before it hits the ground. So it's really a final height of 0. Notice if I calculate the potential and the kinetic at the top and the bottom, they will not be the same. So let's find what the final and the initial. The final is equal to what? The potential energy. Sound noise. And the kinetic energy. And the potential energy, the final is the mass, gravity, y final, kinetic energy 1/2, the mass, and the final velocity squared. The mass of the leaf is 0.017 when you convert that to kilogram. Gravity is 9.8. Final height is 0. 1/2. The mass 0.017. Final velocity, which is what? 1.3 squared. So in this case, this is a 0. And the result is 1.3, turn it on, 0.5 times 0.014 joules. Let's look at the initial. The initial has potential which is mass, gravity, initial height, plus the kinetic, 1/2 mv squared. Mass 0.017, gravity 9.8, initial height is what, 5.30, kinetic energy 1/2 the mass, and final velocity, initial velocity squared, I mean 0 squared. That's a 0. So let's see what we have. 0.017 times 9.8 times 5.3, 0.883 joules. Notice the work done by non-conservative force is a negative. Has to be a negative work. Why? When the leaf is falling down, which way the wind pushing? Upward. And which way is it moving? Down, right? Pushing up, moving down. 180 degree difference between them. That's why it would be a negative value. It's the final minus the initial. Oh, E, not U. The final minus the initial. And it's going to be 0.883. Oh, the final is which one? The smaller one. 0.014 minus the final 0.883. And we have negative. That means we lost that energy. 0.14 minus, clear, 0.014 minus 0.883. It's negative 0.869 joules. Or 87 joules. So here the wind actually made us lose some of the energy. We lost most of it. Notice we had this much. By that time we get to the bottom, we almost a 0. We almost had none. Excuse me. Thank you. So we went from 0.88 to 0.01. Most of it's gone, lost. Another place where we lose energy, if you jump from a diving board, what happens when you hit the water? As you start to go to the bottom, what is the water doing? It's pushing on you, on your body upward. And that's why you stop after about 4 or 5 feet into the water. You're not going down anymore. If we didn't have the water, you'll keep going all the way till you hit the bottom of that pool. But the water becomes a friction force pushing on you. Friction is non-conservative force. So let's see what happens. Let's take an example on that. We have a 95 kilogram diver. So we have a diver. This is the water here. And the mass of that person is 95 kilogram. Steps of a diving board. Steps off a diving board. Steps off, that means what? Initial velocity is what? 0. The diving board is 3 meters high. So the initial height is 3. If I use the water as reference. Now, the person hits the water, then continue to go. This is the bottom of the water right there, but he never makes it to the bottom of the water. Stops right there. Like velocity here is 0. You don't want to hit the bottom of the pool there. That's not a good pool if you hit the bottom from the diving board. So you start to come down and you stop. The reason you stopped is because of what? The friction force. The diver comes to rest right there. Now, if the work done by the non-conservative, I'm giving you that value, by the friction force, if the work done by that force is equal to negative, because it has to be negative, 5,120 joules, find the depth of the water. Not the depth of the water where he stopped, actually, right there, the distance. How far did he go before he came to full stop? That's what D is, depth. Can you find what D is? Now let's talk about this section here. When he entered the water there. Now I'm assuming this force, I think they're neglecting the wind in this part. I think they're neglecting the wind in this part. If you neglect the wind here, we can find what the velocity right before it hits the ground. So neglect the wind here. Can we find out? Let's look at the top half of the story. If we neglect the wind, can we find out how fast was he moving right before he hits the water? Right there. Can we figure what that is? So let's label this as part A and part 1, part 2. This is part 1. And this is part 2. Let's not look at part 2 yet. Let's just stay with part 1. With part 1, what I know, this is what I know. This is my story. That's part 1. And my question is, what was the velocity before he hits the water? Well, we know the height here is what? 0 if I use the water as reference. If I use the water as reference, my height is 0. If I'm neglecting the wind, that's the only non-conservative force in this area. If I neglect that, that tells me what? We have conservation of energy, which means the energy at the top equals the energy at the bottom. At the top is potential energy plus kinetic energy. At the bottom is potential energy at the bottom plus kinetic energy at the bottom. Potential is mass times gravity times height. 95. Gravity is what? 9.8. Initial height is 3. Kinetic, 1/2 the mass. The velocity squared. The potential mass, 95. Gravity, 9.8. The final height, which is 0. Kinetic, 1/2 the mass, which is 95, times the velocity squared. So this is for part A, or part 1. So let's see what we have. 95 times 9.8 times the 3, 2793 equals 47 0.5 v squared. Can we get what v squared equals to? .58, which means the speed before he hits the water. We know it's coming down, so I'm just going to put the value of that. I can say minus to indicate that's coming down. That's what the minus really is. But the value of that, 7.7, 7.67 meters per second. That's the velocity of the person before he hits the water, or she hits the water. Now let's look at part 2. Let's look at the picture now. When the person, part 2 is once you hit the water, right there. Once you hit the water, what was your velocity when you hit the water now? Do we know what that number is? 7.67. We just calculated that. Right? So that becomes the second part of the story. Once you hit the water, you have a speed of 7.67. It's coming down. Now, if I use this as reference, what is the initial height when you hit the water? D, right? And what's your final height? Zero. So part 2, now we're going to look at part 2 and see what's going on there. There we have a friction. We can't neglect that. I'll get the other one out of the picture because I don't want you to see that. I just want to see this part 2. So here's part 2 now. Let's find E final and E initial. E initial is the potential energy plus the kinetic energy. The potential energy is what? Mass, which is 95, gravity, 9.8. What was the initial height? Is it D, if I use where he stopped as reference? The kinetic energy, 1/2. The mass is 95. The velocity is squared. Let's see what these numbers are. Then the one on the right is 2793. This one is 95 times 9.8. 931D. What's the final energy? Mu final plus K final. Mass 95, gravity 9.8, the height 0. Plus 1/2 the mass, 95, times 0 squared. Why? Velocity is 0. So that's equal to 0. This is from part 2. So we broke the problem into 2 parts. Part 1 is before you hit the water. Part 2, what happens after you hit the water. Now, since you have a friction there, we can't neglect that. It tells us there's a friction. We're losing energy. the definition of work done by non-conservative force, that's the friction force. Our book, it says what? E final minus E initial. We know what that number is that was given to us. Negative 5120. E final, that's 0, minus E initial, which is what? 931D plus 2793. What will happen to two minus signs? They cancel each other out. So 5120 equals 931D plus 2793. Bring this one to this side, you subtracted. (5120) minus 2793. The result is 2327. Can we get how deep you're going to go into the water? Divided by 931. 2.5 meters. .5 meters. So we broke it into before you hit the water and after you hit the water. What's going on there? Let's try one more example. We have a jogger that's running uphill. An 80-kilogram jogger. Here's a young lady. The mass, 80 kilogram. And she's going to run up the hill. Start from rest. So initial velocity is what? 0. Run uphill. And in this case, we have a stiff breeze. Well, stiff breeze, that means what? That means the wind was pushing back on her. So we can't neglect that. At the top of the hill, the jogger has done the work. The top of the hill, it says the work here is equal to, that's what the jogger did, plus, had to do extra work, 1.8 times 10 to the 4th joule. The wind, this is the jogger, so how do we label that? What should we label that? The work done at the top of the hill, the jogger has done the work. We'll call NC1, non-conservative one, of plus, because of the wind. The wind here, another non-conservative force, has done a negative work of 4420 joules. This number is larger than this. You have to do more work to compensate for the wind. We know the jogger speed at the top was, the velocity here is 3.50 meters per second. Find the height of the hill in relation to where you started from, how high that hill is. Okay, look at this. The bottom of the hill. This is this one, initial one. What is the potential plus the kinetic? The potential is mass times gravity times height. 80. Gravity is what? 9.8. And what was the height? If I use this as reference, what is my initial height? 0. Plus the kinetic energy, 1/2 the mass, which is 80. What was the initial velocity of the jogger? 0. Square it. So the initial energy for the jogger on right here will be a 0. When you reach the top, let's look at the final energy, mechanical energy. There's a potential energy. There is a kinetic energy. The potential is mass times gravity times height. 80 times 9.8 times the height, which is h. We're looking for it, right? The kinetic, it's 1/2 the mass, which is 80 times the velocity squared. Let's do the math and see what each number is. 80 times 9.8. It's actually 784H plus 0.5 times 80 times 3.5 squared. 490. Now, we know the work done by non-conservative force is equal to what? E what? E initial minus E final, right? Isn't it? Or E final minus E initial. Yep. E final minus E initial. I'm getting tired too. And here my E final is what? 784H plus 490. Take away from it the 0. And what's the result? 490 plus 784H. Now, let's look at these two numbers. They tell us what the non-conservative force is. There's two of them. One is positive, one is negative. So what is the work done by the non-conservative forces from these two numbers? It is the plus 1.8 times 10 to the fourth minus the 4420. 1.8 e to the 4 minus 4420, which is 13580. Well, this value should equal to what? Shouldn't that value equal to this number? So that should equal to what? To the 490 plus the 784H. That's this value. So let's subtract 490 from it. It says 13090 should equal 784H. Can we find what the height of that hill here? It is almost 16.7 meters. See, the person has to give some energy to climb that hill. That's why, just like the engine of a car, he had to supply. You have to supply. If you're running, you have to supply that much energy to make it up the hill. You're also losing energy to that wind. You don't have conservation of energy here. First, there's a friction between your feet and the ground. When you're running, you need that friction. You know it's there. So you have to supply. That's what that's telling you. The person supplied that much energy with their feet pushing. But also they were losing energy of the wind pushing back. So the net result, the person supplied that much energy. That should equal to the difference between them. Now you can find what H is. So when you add non-conservative forces, friction, all that, it changes the problem a little bit there.